Good, we're live. Then almost ready to go. Wrapped up in the cables. Okay, let me start by recapping a little bit what we've covered last time. And there was a little bit left on the introductory part. So we basically talked about complexity classes based on randomized algorithms. We've seen that they are sometimes more powerful than non-randomized algorithms, deterministic algorithms. And now we're taking the perspective of the big P versus NP question, polynomial versus probably not polynomial. What can we say about randomization in this context? And this might come up later, so it's maybe good to remind ourselves. We only have 3 output values here that are relevant. Accept the input, reject the input, or something failed, I can't say, because we're looking at decision problems. And remember that, at least as an upper bound, it's always true that we can use at most one fresh random bit in each time step on our probabilistic Turing machines. And then we define these 3 main classes of randomized complexity with increasing power. You'll look at those in the tutorial, in the upcoming tutorial sheet a bit more. But some inclusions are fairly obvious because we allow more and more errors in the computation, so it becomes easier and easier. You go from CPP to BPP to PP to build algorithms for a specific language. We'll hear a lot today about BPP. Turns out to be the most interesting class, basically because PP is somewhat broken, as we've seen last time. It includes all of NP, and so probably not any interesting practical algorithms just because it's too powerful. And on the other hand, BPP already seems to be handleable in a specific way. And CPP is still useful. The notion of Las Vegas algorithms is useful for practical purposes because it often gives you much stronger guarantees. We've seen that with the probability amplifications and so on. But from a complexity theory standpoint, the most relevant class is BPP here. But right, so CPP is for Las Vegas algorithms, BPP for Monte Carlo, and specifically bounded error. That was the difference between those two, and unbounded errors not very useful. We've seen majority voting before, so unless otherwise stated, we'll always assume that BPP means there's an algorithm that accepts with, or produces the correct output, I should say, with probability at least 2/3. Then we've seen this longer proof that NP is a part of PP and co-NP is following the same way. And that's where we left off. As a last addition to this introductory chapter on randomized complexity classes, I want to introduce a notion that we hadn't discussed before in detail, and it really makes more sense for decision problems only. These are the one-sided error algorithms. And it actually naturally happens if you design algorithms that they happen to be one-sided just as a matter of how they're constructed. So let's look at a simplistic example, which is not a valid Monte Carlo algorithm. But just to get the point across that one-sidedness is natural in this case, it can be natural. If you look at the classic satisfiability problem, a randomized algorithm could just guess some assignment and then output whether the formula is satisfied. Now, the probability for this guess to be correct, depending on the formula, could be very, very small. And so it will not be the error guarantee we require for Monte Carlo. But the point is still, if the formula is unsatisfiable, the probability to output incorrectly that it was is 0. There's no way that this algorithm will ever say, yes, it's satisfiable if it isn't, because it always returns the true value of a formula. And so, at least in principle, this sounds like a reasonable thing to exploit, and you'll see this in this week's tutorial sheet, that it helps with amplifying probabilities. The formal definition of the class of algorithms here is the one-sided error Monte Carlo algorithms, and we'll refer to the others then as two-sided error. Just to have that on the slide, two-sided error Monte Carlo are the unrestricted ones that we considered before. If we have a language, it's only really sensible for decision problems. The algorithm has to accept a word that is in the language with probability at least 1/2. And if the word is not in the language, it has to reject it no matter what randomness plays. So acceptance is always correct, but rejection could be a lie because you can falsely reject some of the words in the language. Why this way, not the other way around? You can also define the one-sided error Monte Carlo algorithm for the complement language and talk about that. Can also make sense. Depends on the specific problem, what is more natural. And there's corresponding complexity classes for those two categories as well. These are RP and co-RP. RP is the set of languages where we have such a one-sided error Monte Carlo algorithm, and co-RP is just those where we have it for the complement language. And so again, these are somewhat similar to NP and co-NP in the sense that also there's this asymmetry. For NP, we would say there is a certificate that makes the verifier accept an input if it is a true input. Whereas if the word is not in the language, then it can never output incorrectly, yes it is. It has to reject the input for every possible certificate. So in that sense, RP and NP fit together in their way of breaking symmetries. Now, as you'll show in the exercises, if you take a language that has a one-sided error Monte Carlo algorithm of both kinds, one-sided error for L and L complement, you can turn that into one that is Las Vegas, and vice versa is easy. So in a sense, although superficially RP and co-RP feel a bit like NP and co-NP, they're really quite different. They're much weaker because for NP and co-NP, as a reminder, something you may have seen, we don't know really what happens if you take problems that are in NP and in co-NP. These are kind of awkward problems. They feel like they should maybe be in P, because they have a certificate both for yes and for no. So in both directions, it's easy to certify that an instance is a yes or a no instance if you're given the certificate, but finding the certificate is not clear in general. These are the typical types of problems where we feel they live in between P and NP complete. These tend to be problems that are in this intersection, but it's a big open problem if the intersection really is P or if there's something beyond. So you could say P is here, then we have NP around here and co-NP around here. And whether this bit is empty, that's unknown. Whereas for the randomized equivalence of NP, this is not the case, right? So here clearly I mean, is that obvious that that ZPP is not clear how ZPP relates to P, I guess, up front. It's not clear. But at least you get the equivalent of having no errors. For the rest of this unit, I want to take you on a slightly longer detour through some slightly more recent, but also slightly more involved topics. But I think the main message behind them is so powerful that it's just interesting to look into them, even if at some points we'll not dig through all the technical details. That's the idea of pseudo-random generators. I guess the term will be familiar to programmers. Usually different people mean different things by calling something a pseudo-random generator. Programmers would understand pseudo-random number generators as meaning some relatively simple function that you give a seed, and then it generates randomly looking numbers. And certainly this is the term is inspired by this use, but we'll see that there's some important differences in the details. So you put some random seed in, and you suppose that this is chosen somehow with real randomness. In reality, it's often just the number of seconds since midnight. So it's not actually random by any definition of randomness, but it is different for different runs of the program. And so it could be good enough. And then it generates many more numbers. And one thing that these pseudo-random generators have is that they're actually a deterministic function of the seed. If you keep the seed, if you put the same seed in tomorrow again, you'll get the same pseudo-random numbers. And I think this is where the pseudo comes from. They're not actually random, at least if the seed wasn't really random, then the numbers certainly won't. Even if the seed is random, looking at a lot of those numbers will eventually reveal that it's not random, because they're simply computed from the seed in some more or less sophisticated way to look random. So often these are some linear congruential method at the very simplistic end. And then Mersenne twister is, I guess, somewhere in between, but no longer state of the art either. And you just try to build functions that make numbers that look random according to statistical tests. So usually here we would say a good pseudo-random generator is output passes statistical tests for randomness. And often these are relatively simple things. One simple statistic could be that the number of zeros and ones, if these are binary numbers, should be roughly the same. We don't expect it to be exactly the same. We expect it to be roughly a binomial distribution, maybe. And so it should roughly reflect that distribution. That's the kind of things where this is used, and that's often good enough for, say, numerical simulations. Now here we'll look at this from a different perspective. And to start us off, let's do the intuitive version first. Suppose we have an algorithm from this BPP class, which is a two-sided error Monte Carlo algorithm with bounded error. we also, and because it's BPP, we assume the running time is polynomial. That also means the number of random bits are bounded, because we can only use one random bit in each time step. So the number of different random bits that we can give the algorithm is also bounded. It's 2 to the number of random bits that I'm using. Every bit can be 0 or 1. That's all. So in principle, I can completely de-randomize this algorithm A by just running it on all these possible random seeds. Indeed, our probabilistic Turing machine model didn't even have randomness in itself. It just relied on having this random bit tape being filled with uniform random inputs. So we could simply do that and output the majority as before. Unlike before, this majority has to be exactly correct, because we're trying all possible outputs and we're just picking the one that occurred most often. So if the algorithm is a BPP algorithm, bounded error, two-sided error Monte Carlo algorithm, then this majority must be correct. Of course, this 2 to the random bits is an exponential blowup. That means most of the time this is not interesting. But if, for some reason, the algorithm very scarcely uses random bits, specifically at most c times log n bits, then 2 to that is same as 2 to the log n to the c, and that's n to the c, which is just a polynomial factor. So if all we're looking at is, can we get a polynomial time algorithm from a polynomial randomized algorithm that's deterministic, then here the answer is yes, because that's, again, a polynomial. It's the product of two polynomials. So this sounds like a potential route, except, of course, most randomized algorithms wouldn't just use log n bits, because you can actually do very little with that. Essentially, you can guess one random number between 1 and n, or maybe a constant number of such numbers. But you cannot do many interesting things like guessing, say, a subset of vertices in a graph or anything like that. So typically, they use at least a linear number of random bits. So this seems not to work. The question now is, can we make it work? Because how would a typical algorithm even know whether the bits that it gets are truly random? Among programmers, there's this XKCD that's popular. Of course, randomness is a real tricky thing. Once you decide it, once you chose the random outcome, all randomness is gone. So what does this really mean to need the randomness? If you go back, I mean, maybe you want to philosophize and puzzle over this definition. If you look at what we need for BPP and the de-randomization here is actually quite clear. We just need that this de-randomization works, which means it's okay if the algorithm is somehow wrong or behaves differently for what we put in instead of the real numbers for a few of the runs, but it should be most of the time doing the same. Okay? From the perspective of this kind of more Byzantine working against each other, the algorithm and the pseudo-random number generator, the question of how the algorithm could distinguish random from non-random numbers should also be defined by, can you find a measurable difference in the outputs of the algorithm? So abstractly, we would somehow like to keep inputs that are sufficiently random, whatever that means. And a breakthrough idea in theoretical computer science was this notion of pseudo-random generators in the specific sense we'll see, where we essentially use that an efficient algorithm cannot distinguish them from truly random. And that's a key difference to the more practically focused view on pseudo-random numbers, where you say, okay, there's some statistical tests, and if these all pass, then probably it'll be fine. This is in a way more direct, but also more demanding. You say no efficient algorithm that you could possibly build can distinguish them. That, of course, includes all statistical tests, because all statistical tests I know are such that you can relatively quickly compute them. Maybe there's some that don't fulfill this definition. The key will be to pick a model of computation so that this whole machinery can be made to work. And that's why the whole chapter is a bit of a longer detour. But then the question still is, do these even exist? Like, is this, are we talking about the empty set? Maybe it's not possible to generate many random numbers from just a small seed without efficient algorithms noticing them. In particular, this phrase here may be a bit dangerous, right? If you look at what we want, we can deal with log n truly random bits, then 2 to the log n is still a polynomial with a constant. If you have a linear number of bits, that's exponentially more than log n. So in a way, we're trying to get from very few random bits a lot of bits, exponentially many more, so that you still cannot distinguish them by any efficient algorithm. Sounds like a wishful thinking land promise that maybe doesn't exist. The somewhat surprising answer that goes hand in hand with this theory is that we have strong evidence that these should exist or might exist. There's no proof, but there's also no proof that NP-hard problems are really hard. It's roughly in the same vein, and we'll rely again on some complexity theory assumptions, but is likely that they exist. Before we define formally what pseudo-random number generators are in this context, I said we have to pick a convenient model of computation. And maybe this is not the only one that can be made to work, but it seems to make some of the proofs tick. And so we're going to dive a bit into this. That's the model of Boolean circuits. The reason, again, here is just for random numbers generators. That's the purpose to introduce it here as an alternative to Turing machines. It does come up in complexity theory in many places as a convenient alternative to look at things. It actually popped up very briefly in the FPT chapter for WP hardness. The right notion was the weighted SAT problem on circuits. We didn't properly define things there because we only needed the intuition. But now let's do it a little more carefully so that we can at least define some of the notions. What's a Boolean circuit? I drew the picture back then. Let me just make up some arbitrary example to make the definition clear. As in a Boolean formula, you have some inputs. These could be just variables. And then you have different gates. You can have a NOT gate that takes the value that you get in and outputs the negation. Or you can have an AND gate. So maybe these two go in here. And then you can have an OR gate that takes the output of this one. But maybe I have an OR gate that takes the output of this one and takes variable x1 as well. And we feed x3 in here, and then we do another AND. Okay, I'm probably making up a not so interesting function. And then we'll have an output somehow marked. That's the only sink. So formally, it's just a directed graph. an acyclic graph. Otherwise, you can't properly define the function computed. It needs to have a single sink. I called it C, so let's call it C. It's called C because capital C is the circuit, because this little c represents the output. And then we have gates in this, for Boolean circuits, somewhat arbitrarily fixed to be and or not. But that's just the way we will define them. And crucially, we'll restrict ourselves here to the gates having a fixed fan out, to and in, to out. In general, you could build circuits where you allow many more inputs, but then you get different types of sizes for the circuit. And that's going to be the next crucial bit. So I hope intuitively is somewhat clear how these work. They're very close to how semiconductor circuits really are built, at least the one abstraction level up. The value computed by such a circuit is just recursively computed. You put the variables in the variable vertices, and then you evaluate in a kind of traversal through the graph. You can assign each vertex a value. So let's maybe do that here. So here, x1, that becomes 0 after the negation. Then let's do this OR gate. There's a 1 going in from here, and another thing that we haven't computed yet. So here's an AND between 0 and that's a 0. So there's a 0 going in for this OR gate, but OR is still 1. x3 is 0, and this is a 0 still, so this OR gate is 0. So the AND gets 1 and 0, output 0. So in the end, the output here, the computed value is 0 or false. And you can define this just over the graph. The crucial thing about circuits is their size, which is just the number of gadgets, or the number of gates, I should say, number of vertices in the graph. Whether or not you count the number of variables in this here, I guess I'm not fussy about. So let's say it's just all the vertices in the circuit. That's just the definition. And we'll connect it to some other things later. Every circuit that you can write down will compute some Boolean function. If it has n variables and sources, then it will compute a Boolean function with an input from 0, 1 to the n, and it'll output a single bit. And that's the function computed by the circuit. And then we can define the first non-trivial thing, the circuit complexity of a Boolean function. If you give me an arbitrary Boolean function, you can ask me, what's the smallest circuit that computes this function? And that turns out to be a very hard question in general. Some Boolean functions obviously allow a specific circuit, and then maybe that's so small that you can prove that there's no smaller. But for many other functions, we feel like you cannot build a small circuit, but we can also not prove it. We don't know whether it's possible to substantially shrink the circuit. Here's a concrete example just to demonstrate some concepts, and also this size, the circuit complexity. So classical function in this area, the parity function, just computes how many bits, well, is there an odd number of 1 bits in the input? So essentially, it's taking just the XOR of all the inputs. And you can conveniently write this as just the sum modulo 2. It's a very simple function, but it turns out it's not so convenient to write a Boolean formula for this. First of all, XOR is associative because it's the addition in this ring modulo 2. So you can always split off the last XOR, say. You can rewrite XOR using the standard Boolean basis of AND, OR, NOT. And so this uses 5 circuit gates. So you can, by iterating this construction, splitting of the last variable, you can build a circuit that uses roughly 5 AND gates. And people have played this game to reduce the constant 5 a little bit. So 5n is not the best possible. You can be a little smarter, but not much, just a small constant factor better. By contrast, if you look at Boolean formulas, it seems not so clear how to make a small formula. Indeed, the obvious way how we build it here with a circuit, if you replace the last XOR by this equivalent expression, you're using the one smaller formula twice. In a circuit, that's fine, because you can just take the output from the previous part and use it twice. But for a Boolean formula, this is not going to work. And so if you expand that, you actually get an exponential blowup. Now, of course, you can be smarter. One way to, if you have an n-fold operation and it's associative, of course, you can break it up at any point. It doesn't have to be the last or the first. And so maybe it's much more natural to say I'm taking parentheses around the middle instead of splitting off one thing if I'm running into this kind of issue. And so you can use this recursion. The number of bits is odd if the first half is even and the second half is odd, or vice versa. That's exactly what this formula expresses. And then you can reduce the size of this Boolean formula to n squared roughly. And that seems to be it. I think it's not, I'm not sure if that's proven, but it seems not possible to do a smaller formula over this basis. So you see already here that circuits are more powerful because they allow reusing calculations. They can substantially expand what you can express with formulas. That was just a little excursion to make that point. That's why in the previous chapter, it made a difference whether we say satisfiability of a Boolean circuit or satisfiability of a Boolean formula. The input is smaller if you allow circuits, and that makes the problem harder. But you can also use circuits as first-class citizens as a computational model. If you think about accepting a language over some alphabet, you fix some encoding of that language into binary. The binary representation is fed into the input variables of a Boolean circuit. And then the output of the circuit can be yes, accept, or no, reject. Right? If you do that, you can get the class P/poly, which is the class of all polynomial-sized circuit solvable problems. So it's all functions or all languages, because the Boolean functions is equivalent, that can be computed with polynomial-sized circuits, where if the function is a general problem restricted to inputs of size n, only needs a circuit of size n to the c. Some obvious thing, like a Turing machine can always simulate the circuit. By just inserting the variables and outputting the output. But there's a slight catch. We can do this for a fixed input size. But what this statement here really says is that for every n, there is some circuit, and it could be a different circuit for every n. I'm just going to write f restricted to inputs of size 0, 1 to the n. And the size of Cn should be polynomial. And if I'm fixing a specific input size, then I can always take a Turing machine that just takes the circuit as an input and simulates the evaluation. Interestingly, you can do the other direction too. You can take any Turing machine that runs in time t of n, and on size n inputs, and you can turn it into a circuit that computes the same function, and you get a slight blow up in the size. You get squared the size of the time. There's two reasons why I'm listing this here. We're not going to prove it. It needs a certain normal form for Turing machines. That's not so relevant for us. First of all, you can transform any Turing machine into a circuit. And what happens is that the time of the Turing machine turns into the size of the circuit. All right, so you should keep this in mind, that the size of a circuit is really the equivalent of the time taken by a Turing machine. And think of the simulation if you go the other way around. If you have a circuit and you want to evaluate it by a Turing machine, you have to go through every vertex and compute. If you do it in a smart order, you can do it in linear time. You have to do the calculation for every vertex in this directed graph, and then you receive the output. So the time you spend for that is the size of the circuit. And you can go the other way around, which is a non-trivial proof, but I'll just state that here as a fact. Now, as I said before, this class of functions, p/poly, is a bit awkward because you're allowed to design a different circuit for every input size. And that also means you can cheat in specific ways. In particular, this p/poly contains a few problems that you shouldn't be able to compute in a reasonable model of computation. It contains certain broken versions of the halting problem. But really what's behind this is just that any unary language where any language that's a subset of just having 1 to the n for all n, meaning it has a single word of every length if it has one. It has at most one word of every length. These are trivially in poly, p/poly, because restricted to 1n, the language is trivial. You just check if the input is all ones. But it turns out you can encode certain halting problems into such a language. So it's a bit of a strange model of computation for general purposes. All right. The other bit is not completely without bounds. Probably NP is not a subset of p/poly, which means these circuits cannot simulate non-determinism. That's not a proof, but it's not a proof in the same way as we don't know whether NP is not a subset of P. It could be equal. So it's not so surprising, but there's a slightly different assumption behind this. So I guess if NP was a subset of P poly, it wouldn't directly imply that P is not equals NP. It would just make the polynomial hierarchy collapse. What's known about these complexities of functions is that it's a bit paradoxical. If you take a random Boolean function generated by picking for every input a random 0-1 output, you're going to end up with functions that require exponential size circuits almost all the time. And that follows just from a simple counting argument. But at the same time, for any kind of interesting functions that we look at, specific functions, it seems incredibly hard to prove any meaningful circuit lower bounds. And the it sounds first like a contradiction, but the point is that the first statement really is about functions that wouldn't have been efficient to compute. The only way to compute them is to run an exponential size circuit. So these are not in P and not even in NP, most likely at least, unless yeah, the most likely not in NP. I think that's even provable. Whereas these functions that we care about, they tend to be functions that are efficiently computable because they have some specific structure. At least we want them to be in NP. And if you think about this for a bit more, then you see that proving an exponential circuit lower bound for any function in NP would immediately imply that P is not equals NP. So that's going to be very hard to do. And on the other hand, the explicit lower bounds that are known, like for the parity function, that's roughly the best we have. Linear in N as the circuit lower bounds is the typical kind of result. And that's a lot of slack between those two, obviously. Now for our pseudo-random generators that we'll come to on the next slide, we'll need a slightly different notion of computing a function. I should really have put this Monte Carlo circuits here in quotes because it's not exactly that. It's rather an average case thing. So the hardness of a function, or the definition before here, definition 810, circuit complexity of a function is just the smallest circuit that computes the function full stop. Now we're going to weaken that by saying, what's the smallest circuit that computes the function at least on most of the possible inputs? And so you can quantify what most means. That's this rho. It's if you pick the inputs uniformly at random, then you want a rho fraction of all these inputs to be computed correctly via some circuit C. And then we say that this rho average case hardness of a function is just the size S of a circuit, so that all the circuits that are not larger than S can only get a rho fraction, can get less of a rho fraction correct. There's a bit many negations involved. But the point is, if you want to compute a function with higher and higher confidence for more and more inputs, you're going to need to represent it more precisely, and that's going to need a larger circuit. So I guess it makes sense that this average hardness goes up with a larger rho. And that's the average hardness. So you don't need to compute the function for every input, just for most of them. And then a slightly curious notion that just makes sure we don't have another parameter flying around is this average case hardness of a function. And that's defined as the maximum of these terms. So in a way, you're using the same parameter for the size of the circuit and for the guarantee that you have for the confidence threshold. You always want to be correct at least half of the time, but then how much above the half of the time you let that go down with larger S. And so in a way, again, it makes sense that this maximum exists, because with larger S, you allow more circuits and you allow them to have more errors. And it's kind of putting the trade-off between these two on a single line. This may look really a bit arbitrary, and in a way the definition, I suppose, is inspired from its uses later. But intuitively, it's a way of saying how complicated a function is in this average case sense. A function is complicated in this sense, so it has a large average case hardness if really you need a big circuit for most of its inputs. All right. And here's the key hypothesis that we'll rely on. This is our equivalent of P is not equal NP. We'll hypothesize that there is a function. We can actually slightly weaken this part, but a function that's reasonable to compute in general, but whose average case hardness is still exponential. Now let me make sure I'm saying this in writing twice and verbally as well. This is not proven. It's a working hypothesis, same as P not equals NP. It's widely believed because we'll have some evidence for it in a second, but it is not proven. We don't know whether that's true. Okay, but that's what we'll run from. There's two bits that make it somewhat plausible that this could exist. Number one is a lengthy excursion of its own that I didn't want to go into. But you can show if there's any function where the worst case hardness is large, so where you need a large circuit for all possible inputs, then you can actually construct some other function. I shouldn't have put the same f here. It's a different function, say g, where the average hardness is also high. And that's maybe somewhat surprising. It's a clever construction. But that only helps us if there are functions that have high worst case complexity. And these we don't know, but again, it looks like things like 3-SAT, if you represent that problem as a language and encode it in circuits, that probably needs exponential size circuits. That's roughly like the exponential time hypothesis. It's not formally equivalent in any sense I know of, but I feel in spirit it's similar. It's roughly saying you need exponential time for 3-SAT, and it turns out for circuits, there's no reason to believe that you get an enormous speed up from doing it on circuits as opposed to on Turing machines. And there's other candidates for this part. So it seems relatively strongly supported, this hypothesis. Not quite as strong as P not equals NP, but somewhere in that range. So maybe we can assume that for now and work from there. And so that brings us to the key definition for this part, which is what do we mean by pseudo-random bits? That's coming back to the beginning. And the formal definition here is essentially using circuits instead of fast programs. We call some fixed string of m bits S epsilon pseudo-random if every circuit up to size S will lead to the same result for most of the inputs. So if you put into the circuit a uniformly random chosen input and R, then the output will be with probability epsilon only different, which means only for an epsilon fraction of all possible inputs can you can the circuit differ on that input from the circuit. Holy cow. Is there an equals 1 missing? So if the circuit on R outputs 1, then it should output 1 for the truly random inputs. And the probability here is over U, right, over the random inputs. So whenever you use those inputs in a small enough circuit, you cannot distinguish them with probability more than epsilon from truly random bits. That's the thing. And again, remember that small circuit means fast algorithms. So it's the equivalent of the, it's an instantiation of the intuitive definition, but it uses circuits of a specific size. This is for a fixed bit vector r, which is in general not what we want. We want something that can generate bits and of arbitrary size. So the pseudo-random generator in its full beauty is a function g that gets seeds of a certain size, L, and outputs a much longer bit string, S of G of the input of size S of L. And we want that it is computable in exponential time. Sounds maybe weird, but that's good enough for what we want. Its output is always S of the input size, so it's increasing the input by exactly the same amount each time. And its output is pseudo-random in the above sense. And arbitrarily, we pick 10% error chance for the pseudo-randomness from above the epsilon. And the size of the circuit is cubed the size of the blow-up that we have. So we make out of L, we make S of L pseudo-random bits. And we need those to be pseudo-random up to a circuit size of S of L cubed. A lot of seemingly arbitrary constants, and some of them, the 10 and the 3, are somewhat arbitrary. There's different choices. These just turn out to be convenient for the proofs. Okay, so far, not much has happened to the intuitive definition, except that we call something pseudo-random specifically if there's no small circuit that distinguishes it from actual random. And a pseudo-random generator has these parameters that make it a bit unwieldy. But the whole beauty is to bring everything into one parameter, and that's this blow-up. How many more random bits can I generate out of L seed bits? And then all of the rest is expressed in terms of this function S of L. All right, let's do a short break, and I'll see how far we get. Yeah, that we certainly can do. Das war der halbwegs vernünftige Teil, das noch nicht so eklig. Ich weiß nicht, Circuits sind ein bisschen seltsam. Aber wir haben jetzt eigentlich noch keine tiefen Resultate darüber hergeleitet. Ich habe nur alles Mögliche zitiert. Ja. Eine Version sollte online sein. Ja, ich habe, oh, okay, Moment, das sind nur die alten. Und das ist irgendwie nicht hochgeladen. Okay, jetzt ist die immer aktualisiert, dauert mal kurz, aber. Ich glaube, auf der alten, naja, da war noch eine Zwischenversion. Das ist seltsam. Warum ist die nicht oben gelandet? Was jetzt gerade online ist, ist, glaube ich, eine ganz alte Version. Aber ich kann es beurteilen, weil es steht ja unten auf der ersten Seite, oder? Ja, vom 17. Ja, man lernt aus den Fehlern. Ja, seltsam. Also ich hatte die eigentlich schon auf das GitHub Pages Ding gepackt, aber irgendwie kam die nicht in den Commit rein. Aber war sicher mein Fehler. Habe ich halt vergessen mit hinzuzufügen wohl. Ja, das Kapitel ist so ein kleines bisschen ausgeartet. Ich fand das, ich finde das eine schöne Konstruktion. Und man kommt tatsächlich auch im Wesentlichen durch alle Details durch. Aber es ist ein bisschen eine Parameterschlacht. Da gibt es ja zwei Optionen. Entweder man sagt von vornherein nur so, geht irgendwie und wir gucken ganz weg. Das ist eine Option. Vielleicht gibt es irgendwie eine schöne Version, die Parameter noch zu reduzieren. Ein paar habe ich schon zusammengestrichen. Aber es sind noch ein paar übrig. Mal schauen, was hinterher so sagst. Ja, wird uns sicherlich noch morgen auch noch ein Stück beschäftigen. Ah, okay. Put it in the wrong place. Whole page gone. Goodie. Okay, so again, that's the definition for pseudo-random. For the moment, I guess it's good enough if you mostly stick to the intuitive version. And then we'll come back to the formal circuit-based version in the chapter after this. In the next section, we'll look at the implications of having such a pseudo-random generator before worrying about whether or not we have one or how likely it is that these exist. And then we'll look at some constructions. The specific constructions we'll look at in the next section is from Nisan and Victorson, and it's taking exactly what we hypothesized in the previous section, namely that there is some Boolean function that has exponential hardness on average. And we'll show that this indeed implies a very strong pseudo-random generator of essentially an exponential number of bits. So the formal statement we'll show is this. Under the assumption of this hypothesis, and we can actually weaken it a little bit, the hypothesis that f is in NP, but it's good enough if you can just deterministically compute it in some exponential time. It's a weaker requirement, but good enough for the construction. And we need this average on this hard on average, the average hardness to be exponential, expressed as some constant delta here. And then there's some construction that turns this into a pseudo-random generator that also has an exponential blow up in terms of how many bits does it generate from L input bits. And the epsilon depends on this delta. So what can we do with that? Why would we care? The thing is that it implies that BPP is exactly the same as P, which means we can completely de-randomize all possible polynomial time randomized algorithms, at least of this Monte Carlo type. But remember, BPP was already the most liberal version of that made any sense. It was the two-sided version as opposed to any of the one-sided ones, and it allowed bounded errors. But if you weaken that a tiny bit, you already get this PP class that seems way too generous. So in a way, this is the maximal statement you could expect. Randomization of any kind might not help at all for solving polynomial time problems. It doesn't look like there's anything you gain by allowing randomness for the class of languages you can decide in polynomial time. So let's prove this. First of all, we use the previous theorem, the existence of this strong pseudo-random generator, which we'll prove in the next section. And hypothesis, the hypothesis about the hard-on-average functions, that we have a pseudo-random generator with S of L bits out of any L seed bits, and that's an exponential function. That's the first step. Then let's pick an arbitrary language in BPP. That means there is some algorithm A, which runs in polynomial time, definition of BPP, and averaging over the randomness that we give the algorithm, it computes the correct result with probability 2/3. Here, L of x, I'm just using this for the characteristic function of the language L. And remember our probabilistic, so algorithm A here is it's a probabilistic Turing machine. And so it always has these two tapes that we give it as input. One with the actual word that we're checking whether it's in the language or not, and one with the random bits. Okay, and here in this statement, R is truly random bits. And let's use M for the number of random bits that this algorithm A is using. And all we'll really need is that the number of random bits is at most the running time of the algorithm, which is at most some polynomial. Okay. Now we apply the de-randomization trick from before. So out of this probabilistic Turing machine, we construct a deterministic Turing machine where we run A, but on pseudo-random bits, generated with our pseudo-random generator. So we have some seed bits set, but these are only L. And then we generate an exponential larger string G of set using our generator. And if you work out what the parameters have to be, we want that M is covered by S of L. We want the generator to produce enough pseudo-random bits to run our algorithm. And so you pick your L such that this is n to the c. And then what you have to do for that is pick a logarithmic number of bits. And essentially the rest we've already somewhat checked, that then the algorithm runs in polynomial time, because the c divided epsilon is just some constant. So we'll simulate this instead of actually using a random seed, we just go over all possible seeds, generate the long string of random bits, and then run A on all those and do a majority vote. So same idea as for a few slides back for de-randomizing algorithms directly. But what we de-randomize is the seed of the pseudo-random generator, not the entire random bit string. If you check, even though the pseudo-random generator had this statement that it runs in exponential time, that was exponential in L, and that's logarithmic. So again, that's polynomial time. And step 2 only does n to the c different seeds. So the whole thing runs in polynomial time, which means the algorithm that we get from there is a p algorithm. What we still have to check is that it actually computes the right function, that it accepts the right strings. And the intuition that you should keep here in mind is what we change from the standard, from the trivial de-randomization is just that we now use pseudo-random bits instead of going over all possible random bits. And so the intuition should be, this is okay because our algorithm A is relatively efficient, and so it shouldn't be able to distinguish between these pseudo-random bits and the truly random bits that we previously defined it with. More formally, what we'll do is a proof by contradiction. So we assume that it would not correctly compute the language of x. So there must be some input, or actually an infinite sequence of inputs. If there's only finitely many, you could patch it. So there must be an infinite sequence of x's of increasing sizes then, where the algorithm, where B produces the wrong result, which means the majority vote must have failed, which in turn means that if I look at my original A and I use the pseudo-random bits, I have less than 1/2 of, so really B of x was false, right? So the majority vote has failed. Which really means that this probability here must have been less than 1/2. But of course, 1/2 is also less than the stated number there. And that turns out to be the original guarantee of A, and then the slack that we allow as a difference between what an algorithm is doing on the real bits and on the pseudo-random bits. So if B wasn't correct on input x, then we would have this. We would have a different behavior for A on the pseudo-random bits than on the real random bits. And that intuitively means we can distinguish the two, the random bits and the pseudo-random bits. So we have to construct a circuit to do that, because again, pseudo-random was defined. I think it would be lovely to have the definition here again. Maybe just in case the whole thing. I don't think we need all of it, but don't want to run back another time. I'll just put that here. For now, it'll go away when we flip pages, but okay. So the thing is that we have to show to arrive at a contradiction is that somehow we can build a distinguisher. So we have to find a circuit C that's small enough where the difference in behavior is bigger than this 1/10. That's what we pick for epsilon. Okay. Now, intuitively, C is easy. It just computes these things. It computes A on X and random bits. And then the random bits that we put in indeed showed that if you put the pseudo-random bits in, something different came out than when you put the real random bits in. But we also have this input X. And at this point, we're using that we're working with circuits as opposed to Turing machines. because what's really convenient for circuits is that if you have some algorithm A, you can, again, we'll convert that to a circuit in the next step. And it has two inputs, X and R. Then you can just imagine the variables being set to a specific value, and then you just fold it in. And so you can shrink the circuit to what's still variable. So you can hardwire specific inputs to have a specific value. And that's a bit harder to do on Turing machines. I guess you could still kind of try to simulate what the program does if certain positions in the input tape always have the same value. But it's much harder to reason about. So this is the key step where we use the properties of circuits as opposed to some other model of computation. So we don't have a circuit for A, we have a Turing machine, but we can convert that. That's the theorem we've had in the previous section. You can build a circuit that has as size the square of the running time of the Turing machine you put in. And then here that works out to order n to the 2c. And if you make n sufficiently large, which really means here the infinite sequence, for the contradiction, you need that you can have a violation for B for as large inputs as you want. So for sufficiently long x's where B produces the wrong output, this circuit C that we built, n to the 2c with some constant, will be smaller than n to the 3c, which is this threshold from the pseudo-random generator. That's where, again, I still have it, so we could paste it another time. So here we're using this part of the definition. So you have to compare your circuit, the distinguisher, to this size threshold. And because for large enough n it's smaller than the threshold, it means it's a valid counterexample. The circuit we constructed shows that the pseudo-random generator is broken, but we assumed that it is a correct pseudo-random generator, so we arrive at a contradiction. Okay. So that means the assumption was wrong and the majority vote is always correct, maybe up to a finite number of inputs. But this you can patch separately. You can always make a separate algorithm that says, okay, if it's one of these finitely many ones, you give the answer, and that only affects the running time by, I guess, a constant factor, maybe at most. So we've shown a deterministic polynomial time algorithm for the same language. So L is also in P. We started with arbitrary L in BPP, and we've shown L is in P, so the two are the same. I guess formally the other inclusion you'll show in the exercises. So for the moment, since we somewhat, at least I claimed that it's somewhat likely that these hard-on-average functions exist, probably randomization alone will not help us solve NP-hard problems. That's maybe a bad news, but I guess it's important to know, because if nothing's more frustrating than not solving a certain task, like designing an algorithm for a certain problem using a certain technique, and then finding out that there's good evidence that what you tried is actually impossible. So I thought I want to spare you that frustration. And the second bit is, this proof, the last proof we've done, conceptually is not very hard. You just do this de-randomization, and then you observe, well, if the de-randomization was very different from the actual random algorithm, then the pseudo-random bits were not actually behaving as random bits, and so the whole thing breaks. The calculations are a bit tedious, but the intuition isn't hard. So the real heavy lifting seems all to be inside this pseudo-random generator. So I hope I motivated you a bit to look inside what that does, and dig a bit into the magic inside there. we won't make it through the entire thing, but we can do the first. It's basically 2 or 3 steps, depending how you count, and we can certainly do the first one, which is also cool from another reason. So it's another thing I wanted to show. Yeah. All right. In the next section, we'll look at this construction from Nisan and Victorson to construct a specific pseudo-random generator, which seemed to do all the heavy lifting in this previous observation. That again, just to mention that, if we can get the construction in this section right, we have very strong evidence that BPP is the same as P. Again, the intuitive version first is assuming we have some Boolean function that has a high circuit lower bound, specifically this hard on average bound. The higher this function is, then the more pseudo-random bits we can pump out of this function from the same number of truly random seed bits. And so the overall construction actually works even in weaker state with weaker assumptions, where this hardness doesn't necessarily need to be exponential. If it's exponential, we get the full result that we used, and we can completely de-randomize BPP. There's also potential parallel universes in between, where we only know about somewhat weaker functions or somewhat weaker lower bounds on the circuit size of functions, and then we can still get something. My compromise for this section was to not show you the best possible construction for all these intermediate parallel universes, but rather focus on the most interesting case, namely that the full hypothesis is true and BPP can be completely de-randomized. I think it's also fair to mention that Avi Victorson won the Turing Award 2 years back, among other things, for these kind of results. He certainly worked on many other things, but randomization and de-randomization are one of the things that were mentioned in the Laudatio. It again shows the kind of impact that these ideas had. Now, this section specifically, I think I'll exclude all the quantitative parts from the exam, just because it gets a bit too crazy and annoying to memorize. I don't think that's so helpful. And getting all the details right, I don't think adds much. The intuition and the qualitative ideas, I think, are fine. You should be able to get those reproduced, but not the setting of the parameters and all these bits. Just to state what in Aurora and Barak's book is the most sophisticated version of this result. So putting this into quantitative terms is what you get in this theorem. If you have any function where the average case hardness is S, then you could build from that a pseudo-random generator that gets almost S. But you have to take this some constant delta, where you take essentially the power to the delta in the end. So it makes it a little less than S of L, but reasonably close and good enough for our purposes. We'll not actually show this result in its generality. We'll show it, but only for the specific case of our exponential S. The key construction of Nisan and Victorson's generator is actually surprisingly simple. And before going through the formal definition, let me just say, suppose you have seed bits, and you line them up. There's always going to be L seed bits in the parameters that we have. And we want to generate M output bits, which is many more, exponentially more. then there's not so much you can do to get from L to essentially exponential in L. The only real construction you have at your disposal is take subsets. And maybe that's intuitive enough. So you take some subset of, how can I draw this nicer? You take some subset of these. Let me try to do it maybe like this. That's going to get one output bit by applying our function f. That's the key idea. Then you take some other set that gets another bit, but again with function f. Now, this is going to go fine for some, but you're not going to be able to avoid overlapping sets if you want an exponential size down here. Right? There's not enough bits in L. So we'll have potentially overlapping subsets. And we'll take a whole family of subsets of the positions in L. And we'll just output all of these, the sequence of all of these subsets. So take the appropriate indices in the subset and feed that to your hard function f. And that's your sequence of pseudo-random bits. I think after seeing it, it's almost like how else would you do it? It seems like almost the only way that could potentially work. But of course, the crucial ingredient here is this this subset, this collection of subsets. And also, we somehow need to show that by doing this computation with overlapping sets, we don't make the result too predictable. Otherwise, it wouldn't be pseudo-random. So that step is maybe very natural, but the magic comes in the following steps. And the key definition, how they came up with this, is not clear to me. The key definition is to have the right restrictions on these subsets to make everything tick. The general framework is, well, they called it combinatorial design, which is a very non-telling term. It's just a collection of subsets from a set of size L, the seed bits. Each of the sets should have size n. In total, we want m of these subsets, and we want to use a very large m. And then there's a third parameter, which is d, and that's the bound on the intersections. So any two of these subsets should have at most d positions in common from the in total n. And in general, it only makes sense if d is at most n, obviously, and n is at most l, obviously, but we'll need some slack between those numbers for such a thing to exist. So this is just the definition that says if I have a collection of subsets satisfying these properties, then I call it a combinatorial design. But you can easily pick parameters for L, N, and D where no such thing exists. And so with this, we're skating at the boundary of existence. And the concrete set of parameters that always works are in this lemma. This is both existence, but also an algorithm to compute such a design. And it's a lovely kind of, it's ironic that the algorithm itself uses de-randomization, but is based on a probabilistic method proof. That's somehow, this could be from Gödel-Escherbach. Okay, forget it. Maybe you'll follow the joke after the proof. So we're given the parameters n, l, and d as input, and we're supposed to generate all these subsets. Because the output is so big, it's definitely going to take a while. Okay, so we allow ourselves exponential time in L. That's fine. At the very end of the game, L will be logarithmic, so no reason to worry. And the restrictions are that L needs to be substantially bigger than n, and the size the number of outputs, the number of sets in our output set that was called M before is 2 to the D over 10. Again, these constants you can probably play with, but no need to. What you don't yet know, or what you cannot yet see, is that these sets of parameters will make for a suitable pseudo-random generator. That's for tomorrow. But I want to briefly show how to do this construction. The algorithm is incredibly simple. We start with no sets, and then we are bluntly iterating over all possible subsets, and we pick the first that we can add to our set without violating any constraints. And the constraint that's relevant is essentially the intersection constraint. If I already have built a collection of some subsets in my calligraphic eye, then if I take a new subset, it might have too many indices in common with some previous set. But I'm going to allow myself to run through all possible subsets. I have exponential time, so why not? And the first one that has a small enough intersection with all previous sets, I'm going to take. So the only question, this algorithm is obviously correct in that it never produces an output that is not a combinatorial design. But the key is it possible that this algorithm finds enough sets? Why could it not possibly be running into a dead end and be stuck so that no set can be added, but we don't have the number of sets that we wanted? So the thing that we still need to show is that A always succeeds. And look at the algorithm, that there's no randomness, okay? It's deterministic. It just does essentially a brute force approach. But to prove that it works, we'll use the probabilistic method. And I've only vaguely explained what that is before. So this is a good way to show you what it does in action. We'll just, instead of running the actual algorithm, we'll do, instead of going over all subsets, what we'll do is we generate a set at random and show that the probability that this succeeds is not 0. And that's the probabilistic method. That's all it does, really. If you have something to generate, and there's a probability that the random object you build is that object, and the probability is greater than 0, then such an object exists. Otherwise, the probability had to be exactly 0. And here we have some freedom. We pick this random set for each position in the allowable indices. We pick the position with probability 2n divided by L. So on average, we'll have 2 times n elements in the set, but it's also random how many, right? But we make the set, we bias the set to be a bit bigger than we need it. And then this is kind of exercise level, and I'm skipping the math this time. You can show with the standard Chernoff bound, because these are independent and with the same probability. These are just binomial random variables. These involved sizes. The probability that the set that you pick is way too small is very small. At least if n is big enough, certainly this is true, because you're expecting way more. You expect 2n. So half of that you'll most of the time have. And also for any fixed set that you already have, the probability that you have a larger intersection with that set than D is exponentially small. And that comes from this bound on L. So in a way, L is so huge that if you only pick 2n of the positions, and here and there, the fact that many of them overlap is actually not likely. Now that's for one specific set J. In the end, our set capital I, calligraphic I, will have a lot of these sets. And we want that we don't have a large intersection with any of them. So this is the bad event, that we have large intersection. the union of all those bad events is that any of the events, at least one bad thing happens. So we can use the union bound on this. We do the probability that I and a specific j have large intersection. And so we take the union over all j in our calligraphic I. And that's where we use the union bound. It's the size of I times the probability for this, and that's the 1/2 to the minus d over 10. And then if you plug that in, this guy is less or equal to the d over 10. That part just cancels and you get the 1/2 that we have here. So the probability that the new set does not intersect any of the sets at too many positions is at least 1/2. And if you take the two together, we want both of the good things at the same time. We at least have a probability of 0.45 that the new random set is good, that in the sense that it has a small number of intersections with everything before and is large enough. Now it might be too large, but that's actually, you can just remove some of the positions until you're down to size n. That can never add intersections, and then you're done. So the beauty why this analysis here is so easy is that because you're picking things independent and at random, you establish exact and complete symmetry on this universe L, so that it doesn't matter what the current sets look like. You can upper bound the probability to intersect any of them in the same way. So in each of the steps where we add a new set, we have some fixed probability to succeed. Now we need to succeed in every round. So actually the probability for m successes in a row is tiny, but it is non-zero. And so some choice exists for the algorithm to pick, and it'll just find it by brute force. Okay, so that's the probabilistic method in action. Although we're analyzing a non-probabilistic algorithm for a key ingredient in building a pseudo-random generator for de-randomizing algorithms. Cool. And we'll see tomorrow how we are using that in the construction.